Hello everyone. Today let us go further in our magnetic effects of electric current. Today we shall be discussing three important topics. First one, types of magnetic field. Second one, force on a current carrying wire when kept in a magnetic field. And third one, application of this effect. So, our topics for today would be types of magnetic field, number second, force on current carrying conductor when kept in uniform magnetic field. Third one of the most primary application which is very important for our board syllabus also, as 5 marks question tend to come from this topic, which is application of the second point known as DC motor. Let us discuss it one by one. First one, types of magnetic field. What we are focusing over here is the magnetic field due to any current carrying conductor which is uniform or increasing or decreasing. If the current in any conductor is fixed, then the magnetic field formed around this conductor will be a uniform magnetic field. Alright, let's see. From here, applying our Fleming's left hand rule, what do we have? That the magnetic field, when current is going in the upward direction, it will be in anti-clockwise direction. Alright, this kind of field is known as uniform magnetic field. Next one is a field when your current either is increasing or current is either decreasing. That means if the current is increasing, then we will have more number of loops in certain area. Let's suppose this is our area. In this area, we have got 1, 2, 3 lines cutting through it. When current further keeps on increasing, the number of lines through this area will keep on increasing. Number of lines through this area keeps on increasing. That means flux is increasing. When flux is increasing, that means our magnetic field is also increasing. This kind of magnetic field, which keeps on changing as the time passes, is known as non-uniform magnetic field. Here, if I am assuming this area, then even after 1 second, only 2 lines are passing through that area. After 5 seconds, 2 lines will be passing through that area, and even after an hour, only these 2 lines will be passing through that area. So for our uniform magnetic field, our magnetic flux is constant, which implies that magnetic field intensity is also a constant value. Alright. When we talk about the force on current carrying conductor, our topic is that current carrying conductor is kept in a uniform magnetic field. So first let us discuss the applications of uniform magnetic field, then we will be further going towards non-uniform magnetic field. But that we shall be discussing afterwards. Remember, हम लोगों ने ऑयस्टेड के बारे में पढ़ा था. ऑयस्टेड के एक्सपेरिमेंट में क्या किया था? जैसे ही किसी भी कंडक्टर के थ्रू करंट फ्लो कर रहा था, एट दैट टाइम जो यहाँ पर मैग्नेटिक नीडल थी उसमें कुछ डिफ्लेक्शन आया. अब मैग्नेटिक नीडल में जो भी डिफ्लेक्शन आ रहा है that deflection denotes that there is a magnetic field which has been created around that current carrying conductor, and उस magnetic field ने इस needle के ऊपर एक force लगाया. अगर उस magnetic field ने इस needle के ऊपर force लगाया तो ऑयस्टेड के एक्सपेरिमेंट के जस्ट कुछ ही टाइम बाद एम्पियर ने सजेस्ट किया that it could even happen the other way around. How so? हमने एक स्मॉल मैग्नेट को करंट कैरिंग कंडक्टर के पास रखा था and that small magnet experienced a force due to that current carrying conductor. Now, what if we place this current carrying conductor in a uniform magnetic field? Let's suppose here this is a south pole, this is a north pole of our, let's say, horseshoe magnet. Okay, now here we have a constant or uniform magnetic field in which this current carrying conductor is kept. What he observed that this current carrying conductor, when kept in this uniform magnetic field, experienced a force which made it to rotate or which made it to move from its original position. That force is known as magnetic force. Now, let us see about this statement. What we have concluded over here is that a current carrying conductor kept in a uniform magnetic field experience a force on it due to that field. This force is known as magnetic force. What would be the nature of this force? See, this force directly depends on the magnetic field. This force is directly dependent on the amount of current per unit length. Right? This is our current, this was our magnetic field. Whenever this field makes this current carrying conductor move, that force or direction of motion of this conductor is always perpendicular to both our magnetic field and the direction of current. Let's suppose this is a wire of L length. If I is the current per unit length, so total current flowing through that wire will be I into L, and we have got B, so the value of our magnetic force is equal to ILB sin theta. Now, what is this sin theta? Theta is the angle between our current carrying element that is L and B, our magnetic intensity. Now, in this case, the angle between L and B is 90 degree. We already know sin 90 degree is 1. So, when theta is equal to 90 degree, we have our magnetic force applied on the conductor to its maximum value. Now, when theta equals to 0 degree or 180 degree, that is when current carrying wire is kept parallel or anti-parallel to our magnetic field, at that time sin theta will be equal to 0, right? Or in this case only, if magnetic field is equal to 0, which was in our Oester's experiment only, magnetic field around that current carrying conductor was almost 0, almost negligible. At that time, that current carrying conductor experienced no force. Even if B equals to 0 or sin theta equals to 0, at that time also our magnetic force will be 0, Alright. What if instead of a current carrying conductor, we have got a moving charge inside any magnetic field? Let us see that one. This is our magnetic field, uniform magnetic field B. There is a charge, a positive charge I am taking of value Q, which has been thrown inside this magnetic field with a velocity V. Okay, at that time, let's see what the value of our magnetic force that we will get. Look, I equals to what? Q upon T. This we already know. So, if this is the current per unit length, then this be the charge for any unit length, right? Now, let us just substitute the value of I over here. If we just substitute the value of I, the magnetic force becomes Q by T into L into B into sin theta. Combine these two. L by T is what? Our velocity. This becomes QVB sin theta. Okay. Here this theta angle, just like over here, this theta angle was the angle between current carrying element and B. In this case, there is no current carrying element, there is only one charge projected inside our magnetic field. So this theta angle will be angle between V and B. Velocity or direction of motion of our charge and magnetic field. Alright, now in this case also, if the charge is stationary, alright, first let's go to the maximum value case. In this case, when theta equals to 90 degree, same as before, magnetic force will be experienced to its maximum value. Second case, when theta equals to 0 degree or 180 degree, or magnetic field equals to 0, or our velocity is equal to 0. Here what we are doing? Either we project the particle parallel or anti-parallel to our magnetic field, one case, or we just project our particle anywhere in the space where there is no magnetic field, or we have got a particle at rest inside any uniform magnetic field. In all the three cases, the magnetic force so experienced by the particle will be 0. Here, it is for this reason that a charge at rest forms only electric field, not any magnetic field. A charge which is kept in any space having no magnetic field or having no uniform magnetic field will experience no force. There will be nothing that could move that charge. And whenever we are placing that charge in the direction or in opposite direction to a magnetic field, at that time also charge won't be deviated from its path. Alright. Now, since we have already discussed that the direction of this magnetic force will be perpendicular to the direction of motion of charge, also at the same time perpendicular to the direction of our magnetic field. So, in practice, how we are going to get the direction of this magnetic force? For that, we will be using our Fleming's left hand rule. Let us discuss it a little bit, and then we'll be moving on to a few questions related to it. Or Fleming's left hand rule. This rule gives the direction of magnetic force when current carrying conductor is kept perpendicular to our magnetic field. Let our magnetic field be B. Whenever we speak of a current carrying conductor, let us talk about only the total current. Magnetic force noted by capital F. Let us write it down with different colored chalk. Alright, now how we are going to use our Fleming's left hand rule? Just look over the diagram here. If we stretch our first three fingers, thumb, our forefinger and our center finger, such a way that each of them are perpendicular to each other, then when our forefinger points in the direction of magnetic field, at that time the center finger will be pointing towards the direction of current. After that, the direction of our thumb will be giving us our magnetic force. So, in XYZ coordinate system, this be our magnetic force, this be our magnetic field, and towards the Z axis, this be our current. So, just remember it like FBI. It is an American criminal agency, FBI. F means magnetic force by the thumb, B means magnetic field by the forefinger, and I means the direction of current by the center finger. Alright. The statement of Fleming's left hand rule goes like this only. If we are to stretch our left hand first three fingers, the thumb, the forefinger and the center finger, perpendicular to each other in such a way that when forefinger points in the direction of our magnetic field and the center finger points in the direction of the current, at that time the thumb will be pointing in the direction of our magnetic force. That be the statement of Fleming's left hand rule. Alright, let us see a few of questions which focus on finding either the direction of magnetic force. Let me show the direction of magnetic field by this blue colored chalk. We will have, according to this three coordinate system, let us decide our direction: east, west, south, north. Then this will be inside the plane and this will be outside. Let's come over here. This is the direction of magnetic field. Let me show the direction of current carrying wire using orange chalk. This be the direction of our current I. Let's suppose this is I, total current I. Okay. Applying our Fleming's left hand rule. Direction of magnetic field. I am fixing the direction of magnetic field by the forefinger towards east direction. Now rotate your arm such that the direction of your current is shown by the direction of our center finger. Then what is the direction of thumb in this case? Coming outward. So in this case, the force on this current carrying conductor will be this. This will be the direction of our magnetic force. Alright, let's discuss another question. Let's suppose direction of our magnetic field is going inside the plane. This be our magnetic field, and let us say the direction of our current is going in this direction. This is our current carrying conductor. Now, direction of our magnetic force. Again, this is our right hand thumb rule. We have already stretched it in perpendicular, mutually perpendicular directions. Now, if I am fixing the direction of current like this, so for getting the direction of magnetic field about this direction, we need to rotate our hand like this. Now, what is happening? Direction of magnetic field is pointing inward, direction of current is pointing this side. So, direction of our force will be going upward. That is towards the north direction. This will be our direction of force in this case. Let's discuss just one more question related to it. Let's suppose direction of our magnetic field is in downward direction. And our current carrying wire is going inside. This is our current carrying wire. This is our magnetic field. This be our current carrying wire. In this case, the direction of our magnetic force will be how so? Suppose this is our current, right? I have already noted that current is going in the inward direction. Accordingly, I am just rotating my forehand, my left hand, such that my forefinger is now pointing in the direction of magnetic field. When current goes inward and magnetic field is in the downward direction or south direction, at that time the direction of our force is in west direction. So, this will be direction of our force, magnetic force. This is how we will be applying our Fleming's left hand rule to find out the direction of magnetic force in different cases. Now, let's switch on to our third point, that is DC motor. One of the primary application of our magnetic force is a DC motor. Let us discuss the application of magnetic force when current carrying wire is kept in a uniform magnetic field. The most important application is DC motor, which is also important related to our board syllabus. Starting from the DC motor, this is the basic construction of our DC motor. But before switching on to this, let us discuss what a DC motor exactly is. So, in board's exam, if question is given in 5 marks for DC motor, you need to first write down the definition of DC motor, where you will write that it is an electrical device which converts electrical energy into mechanical energy. How so? We have already seen the applications of a DC motor in so many appliances, just like a simple fan or any pump or any kind of rotating cooler, right? In all these applications, we are using a motor where we are converting electrical energy into the rotating or kinetic or simply say mechanical energy. Going from definition, next point to be noted is principle of working. Basically, what principle does it follow to work or to function? Principle principle of working says that whenever a current is flowing through any rectangular coil of our motor, that coil, due to the permanent or uniform magnetic field in which it is kept, experiences a force, and the direction of that force is given to us by Fleming's left-hand rule. So our principle of working will go like, it is based on the principle that whenever a current carrying conductor in a uniform magnetic field, it experiences a force that rotates it. The direction of this force is given by Fleming's left-hand rule. This will be the principle of working. Now, let us switch on to the construction part. In construction part, first draw this schematic diagram of your DC motor. Writing DC motor over here. Alright. What you are seeing over here, you need to write it as it is. Let's start from the topmost part. N and S show the north and south pole of any permanent magnet. That will be our first point. Second one, a rectangular coil A, B, C, D of any conducting material. In most of the cases it is copper material. So you could easily write a rectangular ABCD conducting coil is kept in between this permanent magnet affixed on a shaft where the ends of this coil, these are the ends of this coil, are connected to S1 and S2, and in bracket write down split ring. Here S1 and S2 are our split rings. The split rings S1 and S2 are connected further to carbon brushes B1 and B2. These two are our carbon brushes. Which further are connected via any conducting wire to a battery and a key. This is simply the construction part. Here, if you wish, you may write it down as shaft. You may write it down as source of uniform field, uniform magnetic field. ABCD is again your rectangular coil. Now, when the construction part is over, do mention that split rings act as commutator, because it has got very high probability that the role of carbon brushes or commutator is asked in 2 marks question or 3 marks question. So, split rings act as a commutator, and the role of commutator is to reverse the direction of current in the coil. Okay? This is the role of our commutator. Role of our carbon brushes. Carbon brushes help only in the continuous flow of current through the battery in the coil or through the coil in the battery. So, role of our carbon brushes is for the continuous flow of current through the coil, through the battery into the coil or through the coil into the battery, and role of commutator is to reverse the direction of current in coil. Alright. Okay. Now let's come to our working part. So for our working part, this was our construction. First, let us discuss the working, then whatever we are discussing, we'll be writing it down point-wise in our working part. In a battery, start from here. As soon as the key is closed, the circuit is complete and current starts flowing from battery to B1, from B1 to S1, from S1 to A, B, C, D arms of that coil, from there again to S2, from S2 to B2, then from key to battery again. This is the first path of the current. This will be the first point of our working. Now, for the next point, the parts BC and DA are parallel to this constant magnetic field. This is parallel, this is anti-parallel. So, there will be no magnetic force experienced by this BC and DA part. But for the parts AB and CD, we have current in the left side, that is AB arm. Applying Fleming's left hand rule, this be our second point. From BC and DA, whatever the current is flowing, there will be no magnetic force on them. But on AB arm and CD arm, there will be magnetic force. For the direction of magnetic force, apply Fleming's left hand rule. Let us apply Fleming's left hand rule. So, for our AB arm, the direction of force is inward. Direction of force is inward. So, this AB arm goes inside. Now, for our BC arm, direction of force is outward. Since the direction of force is outward, so if let us consider this coil to be like this end has force inside and this end has force outside. So it will move like this. When our coil is moving like this, that is in our anti-clockwise direction. When it is moving in the anti-clockwise direction, at that time what is happening? This split ring is also moving likewise. After 1/4 revolution, that is at this position of our coil, what will happen? The split ring will be coming like this. So, here what would be happening is basically, you need not mention it in your diagram, but I am doing it to make you understand only. Here, in this case, what will happen? The split ring, after 1/4 rotation, this split ring will be like this, and this split ring will be like this. So ultimately, the split rings have lost the contact with our carbon brushes. When they lose the contact with carbon brushes, at that time what is happening? Since our coil has already gained some momentum, so due to that momentum, this coil will rotate slightly on itself even if after losing contact there is no current in our circuit. When the contact is lost, circuit is open. When the circuit is open, there will be no current. If there is no current, so there won't be any magnetic force applying, right? But due to the momentum, what happens? This coil moves further forward, and so now S1 ring comes in contact with the carbon brush B2 and S2 ring comes in contact with the carbon brush B1. Here this will be S1, this will be S2, and at that point of time what will be happening? Our right side arm, that is CD arm, comes to the left side and our AB arm comes to the right side. So this be our AB arm, this be our CD arm. Now after half revolution, what happened? Now the current in the CD arm starts flowing in the upward direction and in the AB arm in the downward direction. Once the current flowing through both the arms get reversed, so direction of magnetic force will also be reversed in these two arms. So again CD arm now will be forced to go inward direction and AB arm will be forced to come in the forward direction. This will cause our coil to rotate continuously in our anti-clockwise direction only. This is basically the working of our DC motor. After that, in the last point you need to write down, as the steps repeat, our coil continues to rotate in the anti-clockwise direction only. So we have already noticed that the role of our split ring was to reverse the direction of our current in the coil, and the role of our carbon brushes, as soon as the split rings exchanged their positions and came in contact with our brushes, the role of our carbon brushes was to continue the flow of current, and it again happened, right? So this was the basic working of our DC motor. Now, there is also a probability that in 3 marks question they tend to ask you, what are the modifications in our conventional DC motor that we could do so that they be used commercially? Let's come to that point. Modifications so that they are used commercially. First modification is to use an electromagnet instead of our permanent magnet, because with time permanent magnet could lose its magnetic effect or could lose its magnetism. So first one is using electromagnets, replacing permanent magnet. Second one, or either to enhance the power of our motor, we could just increase the number of loops in the coil. Third one, for the shaft part, shaft is nothing but a simple rod on which our coil is being wrapped up. So for the shaft part, we could use a soft iron core. The structure of our coil plus shaft made of soft iron core is known as armature, which ultimately helps in enhancing the efficiency or power of our DC motor. So, this was the part of our DC motor, which was simply the application of the force experienced by a current carrying wire when kept in uniform magnetic field. In the next class, let's discuss what happens when current carrying wire is kept in a non-uniform magnetic field, or what happens when simply a conductor is kept in a non-uniform magnetic field. So that bit, thank you.